Hello everybody and welcome to chapter number 7 in statics. This is Professor Algara. I'm going to be talking today about internal forces. Like I said in my previous chapter 5, 6 and 7 are very close to each other. And actually, as far as static goes, the only thing that we'll be covering of chapter number 7 will be internal forces. How do we use them to analyze the structural members. Right here on Blackboard, I have posted also a video of moment and shear and moment diagrams. They're not part of the statics, but I just added them so you can start seeing where are they and how do we use them for material analysis. Okay, but like I said, will not be part of the class. So some of the applications, so beams, we've been talking about trusses and a lot of forces and reactions and things like that, but as far as beams go, there are structural members designed to support loads applied perpendicular to their axis. Beams can be used to support the span of bridges. They're often thicker than the supports. They're often thicker at the supports than the center of the span. What we'll be studying in this lesson, and it's all the internal forces that are very important for designing these kind of elements. So now we'll be introduced to new topics, but they're very similar and connected to what we have studied. The design of any structural member requires finding the forces acting within the material to make sure that the material can stand the loads. So that's more into the design part, and that's very important. So for example, with the pictures that we have right here, we need to calculate internal forces that are acting on the section B right here. In order for us to do that, the first thing we need to do is to calculate the support reactions that are acting right here, and that's what we do. We get AY and DY, we need to calculate them, and once we have the value of those, we will have to break the part into two. By breaking the part into two, we'll be developing some internal forces, and those internal forces is the ones that we're about to discuss. Once you have the internal forces, and you will be able to study the beam, the left side of the beam, which at the end will be exactly the whole beam. In two-dimensional cases, typical internal loads are normal and axial forces, normal acting perpendicular to the section, shear forces acting along the surface, and bending moment. The loads on the left and the right sides of the section B are equal in magnitude but opposite in direction. This is because when the two sides are reconnected and the net loads are zero at that section. So as you break up the part between left and right, you will be developing some internal forces. The internal forces will have one direction, and the ones on the other side will have the opposite direction. So when we connect them together, the net force will be zero. And this is very similar to what we have talked in the past. We talk about reactions at the supports and everything, or the reactions that are connected into this direction, but now we're talking about beams and not trusses. So three forces will be developed. One would be the normal force, which will be perpendicular to the cross-sectional area, then the shear force, which is this one, and then the bending moment. Okay, make sure when you create them or when you put those forces into the section that you're breaking up, then you put the same one on the opposite direction on the other side of the beam. So steps for calculating or getting these internal forces. So first we need to take an imaginary cut at the place where you need to determine the internal forces, then decide which resulting section or piece will be easier to analyze, and that's directly connected to everything that we have taught. You will look at the exercise or the case, and you will see where you have more unknowns, and based on that you will make your decision. If you decide to go with the harder side, then that will be fine too. If necessary, we need to calculate any support reactions or joint forces by drawing the free body diagram in the entire structure, and then solve this for the unknowns. This is very similar to what we have done before. Then After that is calculated, we need to draw a free body diagram on the piece of the structure that you've decided to analyze, and remember that you need to show the internal loads. And then after that, all you have to do is to apply the equations of equilibrium in order to solve for the unknowns. Okay, sum of forces in the y, sum of forces in the x, and sum of moment. And as always, we're gonna have an example. Okay, so let's say you have the following being right here. We need to find internal forces at point 0 right here. All we have to do is just follow the procedure that we just discussed. If we take an imaginary cut right here in B, it'll be easier to work with the section that has only the support B, because it has less unknowns. But don't forget that you will have to calculate the reactions at the support. In order for you to do that, you will have to look at the whole structure, and then apply the equations. So the first thing we need to do is to convert or calculate, from a distributed load into a single one. And it's a rectangle, so it's the base times the height, and then it'll be located right in the center. So if it's 6, it'll be 3 from the left side or from point A. Then we have the support reaction right here, which is this one, and then the support reactions at B. So now we only need to calculate Bx and By, because we need that to calculate just the right side as we decided, at the beginning of the exercise. So if I do that, I know that sum of forces in the x direction is equal to 0, and based on that, the only reaction that I have is Bx, and that is equal to 0. And if we want to find By, all we need to do is just do sum of moment at A, so 8 will be cancelled out, and I don't have to worry about that. Don't forget your sign convention, and that's equals to 0. And then this is equals to minus By multiplies by the distance. I don't have to explain you the sign. Of course, you know that By is doing a negative moment. So then plus 18, which is the load, times the distance, which is 3, and that's equals to 0. With this, I get that By it's equals to 6 kP. Okay, so now I have By and Bx, and with that, I will be now ready to analyze only the right side. So as I break up, the beam right here at B, I will create my shear force, then the normal force, and the moment at C, the couple moment that is created just as the result of breaking that up. And for that, I only have 3 unknowns, 1, 2, and 3. And if I want to solve for that, I have the 3 equations of equilibrium that I need to apply. Something very important right here is that it doesn't matter the sign or the sign convention or the direction of the vector that you decide. Of the force. Because at the end of the day, if you get a negative value, it means that it's supposed to go on the other way. I'm pretty sure you're familiar with that now. So as I do sum of forces in the x direction equals 0, the only force is normal, so NC will be equal to 0. So then if I do sum of forces in the y direction equals 0, I will get that I have minus BC, and then minus 6, and that's equals 0. If I solve for BC, I will get that BC it's equals to minus 6 kAp, or you can say that it's 6 going into the opposite direction. Okay, so then sum of forces around C will be equal to 0, and the only force at C that is causing moment will be 6 going down, which is minus 6 multiplied by the distance, which is 4.5, and then you have the couple moment, don't forget that, which is negative according to my sign convention. So this is MC, and that's equals 0. MC will be equals to minus 27, or if you wanna do it differently, then you can say that it's 27 and the direction is clockwise. And that's it. With that, you will solve and get your internal forces. Now you just did what was asked you to do, and you can move on with the exercise. I have another exercise that I wanted to share with you so you can get used to this. Alright, so you've been given with a system right here, and they're telling you to find the internal forces right here at C. Okay, same procedure. You have to break up the mean, and then you will decide whether you want to work with this or you want to work with all this. It doesn't really matter, it's totally up to you. I always go and work with the side that has less elements, so therefore will be this one, but I know that I will need AY and AX. So if I want to calculate AX and AY, I will have to most likely work with the whole being in order to calculate as the, as always present, and then after that I can just cut the bin. So now I just have to use the whole structure to calculate what I need, AX, AY, BY, so that way I can just focus on one side, and let's do that. So I will do sum of forces in the X direction equals 0, and all I have here will be AX plus 400, that's equals 0. So AX will be equals to minus 400 newtons, and I'm not gonna tell you the same thing about the sign. Then all I have to do is to apply sum of moment, and I will do it around B, so that way I don't have to deal with this. So sum of moment around B, obviously with the sign convention, will be equals to 0, and therefore I get minus AY, that has been multiplied by 5, and then minus 400, that has been multiplied by 1.2. How did I get that? Right here, okay? Do the math. And that's equals to 0. So solving this, I get that AY, it's equals to minus 96 newtons. Alright? So once I have what I need, then I can start and breaking up, I can go ahead and break up the bin and then start doing the results. I already have my loads right here. All I have to do is just add the unknowns, as you know, the couple moment, normal, and BC, and just perform the equations of equilibrium. So sum of forces in the X direction, it's equals 0, and I have in the X direction my normal force minus 400 here, and that's equals 0. So normal force will be equals to 400 newtons. So then the sum of forces in the Y direction will be equals to 0, and therefore I have minus 96 minus BC equals 0. So BC will be equals to minus 96 newtons. Okay, or I know that I said I won't repeat it, but I can tell you 96 newton going into the opposite direction, which is up. Alright, and what else do we need? We just need to do sum of moment, and I will do sum of moment around C, and that's equals 0. So the only force that it's doing moment from here will be 96 newtons, that has been multiplied by 1.5, and then plus the moment, It is positive because I assume it to be positive to go with the sign convention, and that's equals 0. So MC will be equals to minus 144 newtons meter, or 144. Okay, so that's it. That's the whole thing. With that, you basically completed the exercise, and then you can move on. So if you have any questions, guys, just go ahead and send me an email. Like I told you, chapter number 4, 5, 6, and 7, they're very close to one another, especially 5, 6, and 7. We're ready for more exercises. Thank you very much for watching, and if you don't have any questions, I will see you in the next video. Thank you.